All right, let's build on the previous notes, which were about synthetic division, with what's called the remainder theorem. So what we're going to do is use the remainder theorem to evaluate polynomials at given values of x. Now that we'll see what that means in a minute. First, we're going to do these two quick pre-examples here. First, we'll divide this polynomial using synthetic division. So if you remember from the previous notes, we put this 2 in the box, write out our polynomials, our coefficients of the polynomial. So 4, 2, 0, and 3. And now we're going to bring down that 4. 4 times 2 is 8. 8 plus 2 is 10. 10 times 2 is 20. 0 plus 20 is 20. 20 times 2 is 40. And we get 43 as a remainder. So we'll just hang on to that for right now. We'll leave that there. We could write out the answer, but for now, we're going to leave that just like that. And then we'll do the next one. So evaluate the function of the given value. We have the same polynomial, 4x cubed plus 2x squared plus 3. We want to know what this equals at an x value of 2. So we're going to put 2 in to each of these x's. Just like this. So 2 cubed is 8. 2 times 2 times 2 is 8. So this is 4 times 8. Plus 2 times 2 is 4. So this is 2 times 4 plus 3. So 4 times 8 is 32. Plus 8 plus 3. This equals 43. Before we get too far into it, let's take a look at these two examples. We get 43 for this polynomial when x is equal to 2. And we got 43 as a remainder when we divided this polynomial by x minus 2. The common numbers here that we should pay attention to are the r values here, the 2, and the remainder, and the answer, 43. So this is one aspect of the remainder theorem. The remainder theorem says when a polynomial, p of x, is divided by a linear polynomial, x minus a, then the remainder is equal to p of a. So this is what we saw above. We put this number here into the polynomial, and it was the same as the remainder when dividing by that same number. So to evaluate a function at a given value, we can just use synthetic division instead of plugging in the number for x. Typically, depending on your polynomial, the synthetic division process is a much faster process than plugging in and evaluating for x that way. So we're going to use synthetic division to evaluate these four functions at these given values. Okay, so for example, 1a, we're going to put 5 in to this polynomial. So we're going to put 5 in the box here. And then our coefficients are 5x squared, negative 3, and 1. Now bring down the 5. 5 times 5 is 25. 25 plus negative 3 is 22. 22 times 5 is 110. Plus 1 is 111. So that is our answer, 111. And that's a much easier process than plugging in 5 and doing 5 squared times 5 minus 3 times 5 is 15. So it's quicker. Example B, we're going to do the same thing. Here we're putting in negative 1 into the function. So 7x cubed, 2x squared, negative 8x, and then we don't have a constant, so we'll put 0. And remember, the remainder box now is our answer box, which is convenient. So bring down the 7. 7 times negative 1 is negative 7, plus 2 is negative 5, times negative 1 is 5, plus negative 8 is negative 3, times negative 1 is 3, plus 0 is 3. So there's our solution, 3. This is a much faster process than plugging in negative 1 and doing all that work, plugging in the x value to get the y value. We can just use synthetic division. and it works out the same. I think we might need a calculator for example C. We are going to put 7 in to the box here, and we have coefficients of 1, 0, 0, -2, and -10. Quite a few missing coefficients there. All right, let's try it. So we're going to bring down our 1. 1 times 7 is 7, plus 0 is 7, times 7 is 49, plus 0 is 49, times 7 is 343, plus -2 is 341, times 7 is 2,387. Minus 10 is 2,377. And there is our answer. Now, if you're ever not sure, you can always check your answer by putting that number in here for x and evaluating. And with this one, it's not too bad. We can go ahead and make sure, since that number was quite large. 7 to the 4th power is 2,401. So it probably means we were right in the right track. So minus 14, that's 2 times 7, minus 10, does give us 2,377. So we were correct in our answer, but it's okay if that kind of a large number gives you a little pause, makes you think, oh, maybe I should check my work. But it was correct in this case. All right, moving on to example D. We're putting in -5, evaluating this polynomial at -5. -1, 3, -1, and -9 for our coefficients. Bring down the -1 times -5 is 5. Add down, we get 8. Times -5 is -40. Plus -1 is -41. Times -5. Let's go ahead and double check. 41 times 5. It's going to be positive 205. Plus -9 is 196. So there is our answer there, 196. So again, to evaluate a polynomial function at a given value of x, we can use the remainder theorem, which allows us to use synthetic division to divide by that number, which will give us a remainder that is our answer.